Okay, so we've talked about how to find eigenvalues, eigenvectors, and eigenspaces in 2 dimensions, and we just want to show that this can also be done in 3 dimensions. The process is really the same, it's just with 3 by 3 matrices, and so the determinants and finding the solutions to the characteristic equation are a little more complicated, but other than that, it's the same process. So let's just take an example and see what the process looks like. So let's say that we've been given this transformation T, it transforms vectors V, and this is the matrix vector product, so this is the matrix A. And of course, the first thing that we want to do, just like with the 2 by 2 case, is we want to find this determinant of lambda times the identity matrix minus A. And so that's going to be equal to, we'll have this determinant here. We'll take lambda multiplied by the identity matrix, but of course it's the 3 by 3 identity matrix, so instead of doing this in separate steps, we know that this is just going to be lambda 0, 0, 0, lambda 0, and then 0, 0, lambda, when we multiply lambda by the identity matrix, and then we subtract out from that our 3 by 3 matrix, so -1, -6, -2, and then 5, 0, 0. And then we just go ahead and combine our 2 matrices here. So when we do, we get lambda minus 4, we get 0 minus 0, 0 minus 1, 0 minus a -1, lambda minus a -6 would be lambda plus 6, 0 minus a -2 would be positive 2, and then 0 minus 5, 0 minus 0, and lambda minus 0 will just give us lambda. Then we need to find the determinant of this. Since the second column has 2 zeros, let's definitely work along the second column to save ourselves some math. So breaking this down into 2 by 2 determinants, the first thing would be 0, this first entry, multiplied by a 2 by 2 determinant. But since that's going to go to 0, we won't really worry about it. Then we're going to have lambda plus 6 times the 2 by 2 determinant. It's going to come from the corners, so lambda minus 4, -1, -5, and lambda. And then the third entry will have a 0, so we'll say 0 multiplied by a 2 by 2 determinant, but again, we won't really worry about it. We just have to make sure we get our signs right. So starting in the upper left-hand corner, we have a positive sign. We go over here, we have a negative sign. And so then going down the second column, we get negative, positive, negative. So negative, positive, negative. These 2 determinants will go to 0, of course. And so we'll just be left with this one here. So we will get lambda plus 6. And then the determinant here of the 2 by 2 is going to be lambda minus 4 times lambda, and then minus -1 times -5, and that'll give us lambda plus 6. And then here, if we multiply out, we'll get lambda times lambda is a lambda squared minus 4 lambda, and then here we'll have -1 times -5 is a positive 5, so we end up with a -5. And then this can actually be factored, so we get lambda plus 6, and then here we'll get lambda minus 5 and lambda plus 1. So from this then, we can say that when we set this equal to 0 to get our characteristic equation and we solve for the values of lambda, we get lambda is equal to, we'll have -1, positive 5, and -6. So let's say -6, -1, and positive 5. Now we can go about the business of finding our eigenspaces. So for the first one, we'll use the lambda -6 value. So we can say the eigenspace for lambda is -6 is going to be the null space of this matrix when we plug in lambda equals -6. But let's just go ahead and set this up, augmenting it with the 0 vector so that we can find the solution here. So here's what that's going to look like. We'll plug -6 into this matrix. -6 minus 4 is a -10. We get 0, -1, and then 1. -6 plus 6 is 0, 2, -5, 0, and then -6. And we'll augment that with the 0 vector, because putting this into reduced row echelon form and finding the solution will give us the vectors that are in the null space, and therefore the vectors that make up the eigenspace for lambda equals -6. So to put this in reduced row echelon form, let's go ahead and swap the first and second rows. And then from here, once we've got these swapped, we'll go ahead and try to clear out the entries in the 2, 1, and 2, 3 positions. So we'll keep our first row the same, and then for the second row, we'll add 10 of the first row to the second row. So we'll say 10 times 1 is 10, plus a -10 is 0. 10 times 0 is 0, plus 0 is 0. 10 times 2 is 20, plus a -1 is 19. And 10 times 0 is 0, plus 0 is 0. Then same thing here, we'll try to add 5 of the first row to the third row. So we'll say 5 times 1 is 5, plus a -5 is 0. 5 times 0 is 0, plus 0 is 0. 5 times 2 is 10, plus a -6 is 4. And 5 times 0 is 0, plus 0 is 0. Now, if we find the pivot entry here in the second row, we'll divide through by 19. That'll give us just a +1 right here. And then if we subtract 2 of the second row from the first row, that will zero out the 2 for us here. We'll end up with 0. And if we subtract 4 of the second row from the third row, we'll end up here with 0. And so then pulling out a system of equations, remember this is V1, V2, and V3, we'll say that we get V1 is equal to 0, and we get V3 is equal to 0. So if we find a solution here, V2 is a free variable, so we can think about this solution as V1, V2, V3 is equal to, V2 is our free variable, so we've got V2 here, and then we know that V1 is 0, that V3 is 0, and V2 has to be equal to 1 times V2. So the eigenspace for lambda equals -6 is the span of the vector 0, 1, 0. So we'll just keep in mind here that it's the span of this vector. Now we want to do this for the other two. We want to look at the eigenspace for lambda is -1, and that's going to be equal to this matrix when we plug in lambda is -1. So -1 minus 4 is a -5, 0, -1, and then 1, -1 plus 6 is a +5, 2, -5, 0, and -1. And we want to actually go ahead and augment that with the 0 vector. Now to put this into reduced row echelon form, let's go ahead and flip the first and second rows. So we'll get 1, 5, 2, and then 0. And then here we'll have -5, 0, -1, 0, and -5, 0, -1, 0. Here what we notice is that we have duplicate rows. So if we subtract one from the other, we can subtract the second row from the third row to replace the third row. When we do, of course, we'll get 0, 0, 0, 0 along the bottom. We can go ahead and add 5 of the first row to the second row. We'll get 5 times 1 is 5, plus a -5 is 0. 5 times 5 is 25, plus 0 is 25. 5 times 2 is 10, plus a -1 is 9. 5 times 0 is 0, plus 0 is 0. Then we'll go ahead and divide through the second row by 25. When we do that, here we're going to get 1. 25 divided by 25 is 1. And here we'll get 9 over 25. So this value will be 9 over 25. And then we'll go ahead and subtract 5 of the second row from the first row to zero out this 1, 2 position over here. So when we do that, let's see what we get. The second and third rows will stay the same. and then we'll get 1 minus 5 times 0 is 1. 5 minus 5 times 1 is 0. 2 minus 5 times 9 over 25, so 2 minus 5 times 9 over 25. Well, in that case, the 5 will cancel. The 25 will become a 5, and we'll be left with 2 minus 9/5. That's 10 over 5 minus 9 over 5, or 1/5. So we'll get 1/5 here, and then we'll get 0. Now we've got this in reduced row echelon form, and so we can pull out a system and say V1 plus 1/5 V3 is 0, and V2 plus 9 over 25 V3 is 0. If we solve for the pivot variables V1 and V2, we end up with V1 equals negative 1/5 V3, and V2 is equal to negative 9 over 25 V3. V3 is our free variable, so the solution then is V1, V2, V3 is equal to the free variable V3 times, for V1, that's negative 1/5, for V2, that's negative 9 over 25, and V3 is 1 times V3. So the span of this vector is what defines the eigenspace for lambda equals negative 1. So let's go ahead and put in negative 1/5, negative 9 over 25, and 1. And lastly, we just need the eigenspace for lambda equals 5. So for lambda equals 5, we'll plug 5 into this matrix here, and we're going to end up with 5 minus 4 is 1, 0, negative 1, 1, 5 plus 6 is 11, 2, negative 5, 0, and 5. And we'll augment that with the 0 vector to find the null space. We'll go ahead and subtract the first row from the second row. So the first row will stay the same. And then for the second row, we'll get 1 minus 1 is 0, 11 minus 0 is 11, 2 minus a negative 1 is 3, and 0 minus 0 is 0. We'll add 5 of the first row to the third row. So 5 times 1 is 5, plus a negative 5 is 0. 5 times 0 is 0, plus 0 is 0. 5 times a negative 1 is a negative 5, plus 5 is 0. And 5 times 0 is 0, plus 0 is 0. And then we'll divide through the second row by 11, or multiply by 1 over 11. So 1, 0, negative 1, and then 0. And then here in the second row, we'll get 0, 1, 3 over 11, 0, and then our row full of zeros. Now we've got this in reduced row echelon form, and we can pull out the system V1 minus V3 equals 0, and then V2 plus 3 over 11 V3 equals 0. If we solve for the pivot variables, we get V1 equals V3, and we get V2 equals negative 3 over 11 V3, and then our solution, V1, V2, V3, is equal to, we take our free variable V3, and then V1 is equal to 1 V3, V2 is equal to negative 3 over 11 V3, and V3 is equal to 1 V3. And so the span of this vector represents the eigenspace for lambda equals 5. So we can collect this one up here. We'll get 1, negative 3 over 11, and 1. And so if we were then to summarize, we would say the eigenspace for lambda is negative 6 is equal to the span of 0, 1, 0. We would say that the eigenspace for lambda is negative 1 is the span of this vector here, negative 1/5, negative 9 over 25, and 1. And then we would say that the eigenspace for lambda equals 5 is the span of 1, negative 3 over 11, and 1. And so those are our 3 eigenspaces. Notice that they're all lines in R3. What this summary is telling us then is that any vector in R3 that lies along the same line as the vector 0, 1, 0, any vector that's collinear with 0, 1, 0, is going to get scaled by -6, which means it's going to get flipped in exactly the opposite direction and multiplied by 6. So its length is going to be 6 times as long, and it's going to point in exactly the opposite direction. But it's going to be parallel or collinear with its original version. That's what happens to any vector that lies along the same line or is parallel to 0, 1, 0. And then similarly, any vector that is parallel to or collinear with this vector, under the transformation t, it'll have the same length, because we have 1 here, but it'll get flipped in exactly the opposite direction. So it'll point 180 degrees the opposite direction. And then any vector that is parallel to this vector, 1, -3/11, 1, any vector that's collinear with that vector will remain pointing in the same direction, because we have a positive eigenvalue here. It'll remain pointing in the same direction, but it'll get scaled up by 5, meaning that its length will get multiplied by 5.